You made it back. My name is Tepo and welcome to Nated Engineering. This is lesson number 6, which is the last lesson on IC engine power machines and 6. And on this lesson, we want to look at the MORSE test. Now, what is the MORSE test? MORSE test is a test we conduct to determine the indicated power of an engine. Remember, there is a formula that we have been using all along to calculate for the indicated power of the engine, which is this formula. Now, we want to look at what is the difference between the two and when can we use which one. Now, we will always use the equation up until it cannot be trusted anymore. What do I mean by trusted anymore? The instrument that is associated with this equation has limits. It cannot be used for high-speed engines, which are engines that have a rotational frequency that exceeds 960 revolutions per minute. This is the limit of the instrument that is associated with this equation. When we have an engine that is exceeding this speed, that's where we will move to the MORSE test. We will always use this equation until it cannot be trusted anymore. That's where we will now move to the MORSE test. That's requirement number 1 for us to be able to say now we will conduct a MORSE test. What's the next one? We can only conduct a MORSE test for a multi-cylinder engine. We can never conduct a MORSE test for an engine with only one cylinder. And by the end of this lesson, you will know why. So that's requirement number 2. We must have a multi-cylinder equation for us to be able to conduct the MORSE test. And now let's conduct a MORSE test and see how it's done. On the board, we are having a basic illustration of a car engine. It's a 4-cylinder engine, and this is our dimanometer. We know we use our dimanometer to calculate for the brake power, which is given by 2 pi nt. This is the mass that is being mounted on our dimanometer. Now we want to conduct the MORSE test. First, we are going to draw a table like this. With 2 rows. It's a 4-stroke engine. It's 1, 2, 3, 2, 5. Okay. Here we will say it's the number, the cylinder number, and here it will be the brake power in kilowatts. We'll say this one is for cylinder number 1, cylinder number 2, cylinder number 3, and cylinder number 4. Now, the first thing that we must calculate is the brake power, which we know is given by 2 pi nt. Let's say we calculate our brake power and we get that it is x kilowatts. We have our brake power. Now we come back to our engine. The brake power that we have is for the engine when all 4 cylinders are operating, or all 4 cylinders are working. And when we calculate for the brake power, we get that the brake power is x kilowatts. Now, what we are going to do is we are going to start with cylinder number 1. We shut down cylinder number 1. Obviously, when we shut down cylinder number 1, that will result in a decrease in the brake power produced by the cylinder to the crankshaft, meaning our brake power will decrease from this. As a result, if the crankshaft was rotating at an angular velocity of W, now due to the decrease of power produced by the engine, this will also decrease. Now what we want to do is, irregardless of what is happening inside the engine, we still want to have the same rotation, the same angular velocity as we were having when all 4 cylinders were working. We come to the dynamometer. Remember, there is a mass that is mounted on the dynamometer. Let's say this is 5 kg. And we say the rotational frequency, the angular velocity rather, was 10 rads per second. Now, as a result of us shutting this down, we got from 10 to 7 rads per second. What we are going to do is, we come to the mass that is in the dynamometer, we reduce it. Let's say we get from 5 to 4 kg. When we reduce the mass that is in the dynamometer, the load in the crankshaft will decrease, causing the speed to go up. Let's say we got from 5 kg to 4 kg and we were able to achieve 8 rads per second. It's not enough, since we are looking to get back to 10 rads per second. We come again and say from 5 to 2 kg, and let's say now we are able to achieve the 10 rads per second. Now, as a result of us reducing the mass that is in the dynamometer, remember we use the dynamometer to calculate the brake power. The brake power is given by 2 pi nt. The torque is given by the radius times the force. Force is given by mass times the gravitational acceleration. We decrease the mass that is in the dynamometer. That mass we are going to calculate for the force which will be used in the torque that will be used to calculate the brake power. Meaning that us decreasing the mass that is used to calculate the torque will result in the brake power decreasing. Now we are no longer having a brake power of X kilowatts because we have decreased the mass that is in the dynamometer. The brake power that we are going to have now will be less than what we had when all the cylinders were active. We take this, let's say we got that our brake power is now A. We put it here. Remember, we shut down cylinder number 1. The brake power and the angular velocity decrease. We want to go back to the original angular velocity. Therefore, we ease the mass. We reduce the mass that is in the dynamometer. As a result, we are able to go back to the original angular velocity. But us reducing the mass caused us to have a decrease in the brake power, which is what we are going to record here. We do the same thing. We reset everything. And we do the same thing for cylinder number 2. Now everything is back to normal. The mass is back to 5. The angular velocity is back to 10. And we start again. We shut down cylinder number 2. It goes down. We ease. Reduce the mass that is in the dynamometer so that we are able to go back to 10 rads per second. And we use that information to calculate the brake power. The value that we get, we put into the table. We say it's B. We do the same thing for cylinder number 3, say it's C, and for cylinder number 4, it's D. Now, what we are going to do is, from our original brake power, we are going to say X, which is our original brake power. when all the cylinders were operating, minus the brake power that we got when cylinder number 1 was shut down, and the mass on the dynamometer reduced to get back to the original angular velocity. So minus it here is A. And this will be the indicated power on cylinder number 1. Cylinder number 1, say just 1. And we come to cylinder number 2. We say the IP on cylinder number 2, which will be X minus B. IP on number 3, X minus C. IP on number 4 is equals to X minus D. Let's say here we've got X, Y, Z. Let's say it's L. Let me write numbers. Let's say it's 1, 2, 3, 4. Now we will say the sum of all these, we add the IP of cylinder number 1, of cylinder number 2, 3, and 4. It's 1, 3, 6, 10. We say the indicated power of the engine is 10 kilowatts. And this is how we calculate for the indicated power of an engine using the MORSE test. And they say this is the estimate, which means it's an approximate value. It's not the exact value. It's the approximate. Using the MORSE test, we are going to get the approximate value, or the approximate indicated power of the engine. And let's do an exercise to see how do we apply this on an exercise. In a trial on a 6-cylinder petrol engine, a MORSE test was carried out to estimate the indicated power of the engine. Running at full load with all cylinders working, the brake power output was 52 kilowatts. The measured brake power output in kilowatts when each cylinder was cut out in 10 and the load reduced to bring the engine back to its original speed are shown in the table. And then they gave us a table recording that, where they have recorded all the information. Use the above data to answer the questions. Number 1, estimate the indicated power IP of the engine. Number 2, estimate the mechanical efficiency of the engine. And this is the information that we are given. They gave us the table where they have already recorded everything. They gave us the original brake power when the engine, they told us it's a 6-cylinder engine, when all the cylinders were active. This is the brake power that we had. We are working with a 6-cylinder engine. And then they tell us the questions. They say we must calculate for the estimate indicated power. This is what we are going to do. Since we already have the information and we have the brake power, we know from here we are going to say indicated power number 1 will be equals to the original brake power, which is 52, minus, we start with number 1, which is 40.5. Here we are going to get 11.5 kilowatts. We go to IP number 2. It's 52 minus 40.2. IP number 3. 52 minus 40.1. IP number 4. 52 in minus 40.6. And IP number 5. 52 minus 40.7, which would be let's write this first. IP number 6, it's 52 minus 40, and the answers here, it's 11.8, 11.9, it's kilowatts, 11.4, 11.4 kilowatts, 11.3 kilowatts, and 11.2, oh sorry, it's 12 kilowatts. And we said the sum of all these IP engine, the sum of all these IP, we will say indicated power 1, 2, 3, 4, 5, 6. The sum gives us the total estimate of the engine, which is 69.9 kilowatts. This is the estimate indicated power of the engine. And then from here, you can continue as usual. We now have the indicated power. The next question, they said, calculate the mechanical efficiency. We know mechanical efficiency is given by the brake power divided by the indicated power times 100. We have the brake power, we have the indicated power. From here, we just substitute 52 it's just 52 divided by 69.9 times 100, which will give us a mechanical efficiency of 74.4%. And that is how we conduct the MORSE test. The reason why you cannot conduct a MORSE test on an engine with only one cylinder is because when you shut down that engine, that one cylinder, the engine will just stop. You need at least 2 cylinders on an engine to perform or to conduct the MORSE test, so that when you shut down one engine, one cylinder, you are able to record the information using the other cylinder. That is the reason why you can only conduct a MORSE test on a multi-cylinder engine. Another thing, pay attention to the information that you are given here in this column, because they might give you the torque, not the brake power. They might give you a torque. This might be the torque in Newton meter. And from here, what you need to do is first come to this equation. Brake power is equals to 2 pi nt. Put the torque here. The rotational frequency will be given. Put the torque here. After, you are able to create another column where you are going to record the brake power for each cylinder. If you are given the torque, you must first calculate for the brake power yourself, and then you come to this stage. That is how we conclude in the IC engine, power machines, and 6. I will see you on the next lesson.